All right, so hello everybody. My name is Hun Chung. I'm an associate professor in the Faculty of Political Science and Economics at Waseda University. And this is basically a short segment that I have extracted from a more longer course that I teach at Waseda University, uh, which is an introduction to social choice theory. So this lecture segment is my lecture on binary relations. And I think binary relations, understanding what binary relation is important for people who do philosophy in general, and also people who work in the areas of PPE. All right, so I hope many of you find this lecture somewhat useful. And if you want to learn more about myself, you may visit my homepage at hunchung.com. And if you have any questions or any comments, you can send me an email at my Gmail address at hunchung1980@gmail.com. Okay. Okay, so let us now try to understand the concept of binary relations. Okay, so in order to understand binary relations, we need to first understand a concept of what's called a Cartesian product. Okay, so what is a Cartesian product? First, let x and y be two sets. Then we're going to use this symbol here. It's the set x times the set y. All right, so it's kind of like you might think of this as multiplications of two sets, right? So we're going to say x times y, that is the Cartesian product of x and y, is going to be defined as follows. Okay, so basically the set x times y is basically a set, and it's a set consisting of ordered pairs. Okay, so it's a set. The elements of the set x times y is basically ordered pairs. So such that the first component of this pair comes from set x, and the second component y comes from set y. Okay, so basically that is the Cartesian product of x and y, or x times y, is the set of all ordered pairs where the first component is an element of x, right, while the second component is an element of y. So here is an example. Suppose that set x consists of two elements, 1 and 2, and suppose that the set y consists of three elements, a, b, and c. Now, the question is, what is the Cartesian product of x over y? So what is x times y? So this will basically consist of ordered pairs such that the first component comes from the set x. So 1a is going to be included, 1b is going to be included, 1c is going to be included, and there will be components where the first element is going to be 2, right? So 2a, 2b, and 2c. Okay? So that will basically consist of the Cartesian product of x times y. Okay, so based on our definition of Cartesian products, let us now try to understand what binary relations are. So a binary relation, and we're going to use B to denote a generic binary relation. So a binary relation between two sets x and y is simply a subset of the Cartesian product between x and y. That is, the binary relation B is going to be a subset of the set of all ordered pairs between x and y, where the first component comes from the set x and the second component comes from the set y. So let B be a binary relation between x and y. So that is B is a subset of x times y. If the ordered pair x and y is an element of the binary relation B, then we're going to say that element x bears the relation B to y. Okay? So, and then we're often going to write x be y, use this symbol here, instead of the symbol that says the ordered pair x and y is an element of B. Okay? And this symbol here is used mainly to make it more intuitive. That it makes it more intuitively easier to understand the specific relationship between x and y. So this basically says that x is related to y by relation B. Okay? So when a binary relation is defined on the Cartesian product of some set to itself, we say that the binary relation B is a relation on, okay? Relation on x, right? So here, the binary relation will basically consist of a set of ordered pairs, which is a subset of the Cartesian product of x to itself. So that's the binary relation, and there are basically two ways to represent a binary relation. One way, all right, so let us illustrate this with a specific example. So let B be a binary relation on U, right? So basically what this is basically saying here is that B is a subset of the Cartesian product of U to itself. And suppose that we have the following. A bears the relation to A bears the relation to B bears the relation to A, B bears the relation to C, and C bears the relation to C. Then we may basically represent this relation B either, right, on the Cartesian plane or directed graphs on the right. So here it is, okay? So both pictures are representation of the binary relation B, and we can see here, all right? So all of these dots here, the 9 dots, represents the Cartesian product of U against itself. So among these 9 dots, the binary relation B is a subset of U times U that picks out certain members while leaving out other members from the Cartesian product of U. And we can see here that this here, the fact that A is related to A, represents this dot over here. A is related to A in this binary relation. The fact that A is related to B, according to binary relation B, is represented by this dot here. So A is related to B, and it is inside this shaded region. B is related to A, corresponds to this. B is related to C, corresponds to this. And C is related to C, is related to this. Okay? So this is one way. This is one way to represent a given binary relation. You can do it on what's called the Cartesian plane. But when you represent a binary relation in this way, the intuitive meaning that a certain element is related to another element by the binary relation is a little bit difficult to grasp intuitively. So instead, we we will also use a different representation to represent binary relation by directed graphs. And the basic thought is that each element in the set U is represented by a dot. So again, the set U consists of three elements, A, B, and C. So there's element A, element B, and element C, which are represented by dots. And what we do is we use directed arrows to basically represent that a given element is related to another element, right? So basically, when we want to represent the fact that A is related to A, this is represented by an arrow that emanates from A and it goes inside A itself, right? So this arrow here is basically represents that A is related to A. So this arrow here, which connects A to B, basically represents the fact that A is related to B. Okay? And the fact that, and this arrow here basically represents the fact that B is related to A by the binary relation B, and same forth, right? So B is related to C is represented by this arrow, and the fact that C is related to itself is represented by an arrow that is pointing towards itself, right? So this is another representation of the binary relation B. And you'll kind of like notice that in comparison to using Cartesian planes, actually it is much more intuitively clear to understand this specific relationship between the elements by using directed graphs. Okay, but it'll be good for you to understand how a given binary relation can be represented in both ways and so forth. Okay, so let us look at learn the various properties of binary relations. Okay, so let B be a binary relation on X, right? And as we have seen, this basically means B is a subset of the Cartesian product of X to itself. Okay? Then we're going to say that the binary relation B is first reflexive if for every element in X, X bears the relation to itself, right? So, in terms of directed graphs, this will basically be if there is an element X, there has to be an arrow pointing to itself. Okay, so there might be many relations that are reflexive. For example, is the same age as, right? So example, is the same age as. Okay, so we can see that everybody is the same age as themselves, right? I am the same age as me. Therefore, the relation is the same age as is reflexive. Okay, so that's what it means. The next relation is irreflexive. So a binary relation is said to be irreflexive if for every element X, X does not bear the relation to itself, right? So what this basically means is that there exists no element that bears the relation to itself. Okay, so for this, for every element, it is not the case that X bears the relation to itself, but as we have seen, this is logically equivalent to the statement that it is not the case that there exists an element in X such that X bears the relation to itself. Okay, so those two things mean the same thing. So when a binary relation is irreflexive, it simply means that there exists no elements that bears the relation to itself. Okay, or you can say that it is not the case that for every element in X, it is not the case that it bears the relation to itself. Okay. Okay, we're going to say that a binary relation is complete if for every X and Y, either X bears the relation to Y or Y bears the relation to X. Okay. And next one is a similar property called totality, right? So this says that for every X and Y in set X, such that if X and Y are different, so X and Y are not the same, then either X bears the relation to itself or Y bears the relation to X. Okay? So the two properties, completeness and totalities, are different, are very similar, but whereas the difference is that whereas completeness applies to every pair of X and Y, totality applies only when X and Y are different, right? So the question is, so here is a basic question. Suppose that a relation is complete does that imply that the relation is total, right? And the answer is yes, right? Because completeness is a more general property. It applies to every pair of elements in X, even when they are the same, right? Meaning that even completeness, if a relation is complete, it also applies when the two elements X and Y are the same, right? Then how about this? Suppose that a relation is total, does this imply that the relation is complete? And think of this for a moment. Pause and try to think of this. And once you're convinced, replay. And the answer is it is not. Okay? And here is a basic example that illustrates this. Suppose that we have element A and element B, and we have this relation here, right? So we can see that this relation is total, right? Because there are only two elements, and for every elements that are different, A and B, either there is a relation between A and B. But we can see that it is not. All right, so I'll use a different color. Let's use blue. So complete, it is not complete. And why is it not complete? The main reason is, although there is a relation between A and B, there is no relation between A to itself and B to itself. So if we add these arrows, then the relation is going to be complete, but without these arrows in itself, it is not complete. Okay? Okay, so the next relation that we will look at is called symmetry. A relation is said to be symmetric if for every X and Y, if X bears the relation to Y, then this implies that Y bears the relation to X. Okay, and here, okay, so here's the three basic set of symmetric relations. So the first one was symmetry, as I just explained. The next one is called asymmetry. And what this basically says is that for every x and y, if x bears the relation to y, then this implies that y does not bear the relation to x. Okay? So we can kind of like rearrange this, and this basically is logically equivalent to saying that it is not the case that x bears the relation to y and y bears the relation to x. Okay? And the reason why these two are logically equivalent comes from the definition of material implication. Okay? So for instance, x bears the relation to y implies it is not the case that y bears the relation to x. By material implication, this is the same as not x be y, or not y be x. Okay? And by De Morgan's law, we can extract the negation sign outside the bracket, and by doing so, the disjunction changes into a conjunction. So this is the same as it is not the case that x bears the relation to y and y bears the relation to x. Okay? And that is basically the reason why this definition and this definition is the same, right? And if you think of it, it'll basically mean intuitive sense, right? So an asymmetric means that there exists no element, there exists no two pair of elements such that the relationship goes both ways. So here is another related relation called anti-symmetry. And according to anti-symmetry, it basically means that for all elements x and y, if x is related to y and y is related to x, then this implies that x and y are the same. Okay? So in real numbers, usually the relation that is asymmetric in the real number system is the greater than. Okay? So if some number is greater than x, if x is greater than y, then this implies that y is not greater than x. Okay? And an anti-symmetric relation in the real number system is greater or equal than, right? So this means that if x is related to y, x is greater or equal to y, and y is greater or equal to x, then this implies that x and y are the same. Okay, right? So here, if x is greater or equal to y, and y is greater or equal to x, you can see that x and y are the same. And similarly, up here, if x is greater than y, then this implies that y is not greater than x. Okay. All right, so the next property is called transitivity. And this basically says, for every three elements, x, y, and z, if x is related to y and y is related to z, then this implies that x is related to z. Okay? So this is transitivity. If x is related to y, y is related to b, then x. So again, there might be a lot of examples of a transitive relation. Say is taller than, right? Say is taller than. right? So if A is taller than B and if B is taller than C, then this implies that A is taller than C. So this implies that the relation is taller than is a transitive relation. There is a negative version of this transitive relation called negative transitivity. And according to this implies that for every three elements x, y, and z, if x is not related to y and y is not related to z, then this implies that x is not related to z. So here we have negative transitivity. Okay, so let us now try to understand these properties of binary relations by using the directed graph representations that we have seen previously. Okay, so let's start. So suppose that we have a set X consisting of just two elements. So this is basically the simplest example that we can think of. And suppose that binary relation B is defined on the set X. Okay. Now, let's look at the first example. Okay, in the first picture here, this represents a reflexive relation. And this is because that we can see that all of the elements bear the relation to itself. So it is reflexive. But now, consider the picture over here, the second picture. This is not reflexive. And why is it not reflexive? The main reason why is that there exists an element B that is not related to itself. Okay, right? So reflexivity basically requires every element to be related to itself. So if there exists some element, at least one element that does not bear the relation to itself, then that is sufficient to show that the relation is not reflexive. Okay? So the picture here shows a relation that is irreflexive. And remember what irreflexive means. When a relation is irreflexive, that basically means that every element does not bear the relation to itself. And we can see here that there are only two elements, A and B. A does not bear the relation to itself, and B does not bear the relation to itself. So the relation is irreflexive. But now, look at this picture over here. This picture shows that the relation is not irreflexive. And why is that? In order for a relation to be reflexive, it means that every element should not bear the relation to itself. Meaning that if there exists an element that bears the relation to itself, then that means that the relation is not irreflexive. And we can see here that the element A bears the relation to itself. Therefore, the relation is not irreflexive, right? So I'll just highlight those as well. Now, consider this picture here. This relation represents a complete relation. So a complete relation, basically, when a relation is complete, that basically says for every pair of two pairs of alternatives, either x and y, either x bears the relation to y or y bears the relation to x. And we can see here that there are two elements, A and B. And for every pair, we can see that there's a relation from one way or the other. So if we choose A and B, we can see that A is related to B and B is related to A. That's okay. So, but you can also see that if we choose the same pair, the same elements to consist of the pair. So if we choose A and A, we can see that A is related to A and B is also related to B. So the relation is complete. But This shows that the relation is not complete. Okay? And why is it not complete? Try to think of yourselves. Why? The reason why it is not complete is that there's no arrow between either A or B or A, right? So if this were the case, then it would be complete. If this were the case, the relation would be complete. And if this were the case, the relation would be complete. But so in order for the relation to be complete, there has to be at least some arrow between A and B. But since A and B does not have any arrows between them, the relation is not complete. Now, here is another example. So this is an example of a relation that is asymmetric. Okay? And remember what asymmetry said? Asymmetry basically said that if some element is related to another element, then that latter element is not related to the former element, the previous element, right? So in other words, a relation is asymmetric, then this implies that there exists no pair of elements such that the relationship goes both ways, right? So we can see here that there's a relation going from A to B, but there is no relation going to B to A. Therefore, it is asymmetric. In contrast, if you look at the picture on the right, we can see that A is related to B, but B is also related to A. But in order for a relation to be asymmetric, if A is related to B, B should not be related to A, or if B is related to A should not be related to B. But since they're related to each other, this means that the relation is not asymmetric. Okay? So it's not asymmetric. This one is not complete and reflexive and so forth. Okay, so let us consider more binary relations. Again, suppose that the set X consists of two elements, A and B, and let B be a binary relation defined on set X. Okay, so here are some more pictures. So consider the first picture on the top left. This picture basically represents a binary relation that is symmetric. Why? You can see that symmetricity basically says that if an element is related to another element, then that other element is also related to the former element. And we can see here that there are two elements, A and B, and we can see that A is related to B, and B is also related to A. Therefore, the relation is symmetric. Now, consider the picture on the right and try to understand why this is not symmetric. Why is it not symmetric? It is not symmetric mainly because symmetricity says that if B is related to A, then A also has to be related to B. But in this picture, we can see that A is not related to B, so it is not symmetric. So in order to make this relation symmetric, we should have an arrow that points from A to B. Now consider the picture on the middle, on the left column. This represents a relation that is transitive. And again, transitivity basically says that if A is related to B and B is related to C, then A is related to C. And we can see here that it is transitive. Now, let's move on to the picture that is on the right. This is not transitive, and the reason why it is not transitive is because although A is related to B and B is related to C, A is not related to C. So in order to make this picture transitive, we must have an arrow that comes out from A and points towards C. Okay? Now consider the picture on the bottom left corner here. So this is a picture that represents a relation that is negatively transitive. And the reason why it is negatively transitive is because you can see that right? So there's no relation between C to A, and there's no relation between B to A, and we can also see that there's no relationship between C to A as well, right? And also you can see that there's no relationship between B to A, but yes, that's the case. Okay. No relationship between C to A, but there's no, so the antecedent is not met there. Okay. So again, when we talk about all right, so before we move that, let's move on to the last picture on the right corner of the bottom row. And this picture represents a situation that is not negatively transitive. And why is that? Try to think for yourself why it is not negatively transitive. Right? The reason why it is not negatively transitive is we can see that there's no relation between A to C, and there's no relationship between C to A, right? But there is a relationship between A to B, right? So it is not negatively transitive. Okay? So we can see that the original definition here of negative transitivity is a little bit cumbersome to actually apply. So that is why, as we will later prove a little bit later, there is a much easier way to check negative transitivity. Okay, and we'll later see how what that is. Okay, so to understand the logical implications of various binary relations, let's look at some basic true or false questions. So let us try to determine whether the following statement is either true or false. So let B be a binary relation on X, and consider the statement. If B is reflexive, B is not reflexive, then B is irreflexive. Okay? So what do you think? Is this true or is it false? Pause for a minute and try to think for yourself before you move on. So what do you think? So to understand this, it will be helpful if we go back to the basic definition of what it means for a binary relation to be reflexive. So the binary relation is reflexive basically means if and only if for all element x in X, X be X. But here, then, what does it mean for a binary relation to be not reflexive? So if a binary relation B is not reflexive, then this basically means it is not the case that for all elements in X, X be X. And we already learned how to negate a quantified sentence here. So we move this negation sign inside the quantifier, and the universal quantifier changes into an existential one. So this is the same as when we move this negation symbol inside, and we have to change the universal quantifier to existential one. So what this turns into is there exists an element in X such that it is not the case, X is not related to X. Okay? And you can kind of basically see that this is different from saying that for all element in X, it is not X is not related to itself, right? So the first statement, which is the statement written on the antecedent, simply says that there exists an element that is not related to itself, whereas the second statement uses a universal quantifier, says that all elements are not related to itself. And this is basically, these two are different, but this is the definition of the binary relation being irreflexive. Right? So again, B being not reflexive is different from B being irreflexive. Okay? So a specific example would be, consider an example in which X consists of two elements, A and B, and consider a case where the relation is like this, okay? So we can see that in this picture here, B is relation on X. So in this picture, we can see that it is not reflexive. And the reason why it is not reflexive is because we can see that although A is related to itself, there exists an element that is not related to itself, namely B. We can also see that it is not irreflexive. And the reason why it is so is because although B is not related to itself, there exists an element that is related to itself, namely A, right? So this is an example that is not reflexive and not irreflexive. So basically, being not reflexive does not imply that the relation is irreflexive. So the answer is false. Sorry, the answer is false. Sorry. The answer is false. Okay. Okay, here is a related and a similar question. And if you understood what I've explained in the previous slide, you should also understand this. So suppose that B is not reflexive. Does that imply that B is reflexive? Again, so it will be helpful if we could understand, if we could go back to the definition of what it means for a binary relation to be irreflexive. So recall that B is irreflexive basically means, by definition, for all elements in X, it is not the case that X is related to X. Okay? So if B is not irreflexive, then this basically means that it is not the case that for all x in x, x is not related to x, okay? But then we can then move the quantifier inside, and we have to change the universal quantifier into existential quantifier. And by doing so, this basically amounts to there exists an element x in x such that it is not the case that x is not related to x. And we can see here we have a double negation here which cancels out. So this basically turns out to mean there exists an x, an element x, that such that x is related to x, okay? And we can see that this is different from saying all elements, for all elements in x, x be x, which is the definition of B is reflexive, right? So what this definition basically says is that just because a binary relation is not irreflexive, it doesn't imply that B is reflexive. And again, the same picture that we have seen in the previous slide gives a counterexample to the statement. So this is a picture in which the relation B is not irreflexive. And the reason why that is so is because there exists an element, namely A, that is related to itself. But we can also see that the relation B is not reflexive. And that is because there exists an element that is not related to itself, namely B. So this statement is also false. Okay, so let's move on. So consider the statement, if B is complete, then B is total. All right, so this is actually something that we have already, that I have briefly explained in the previous slide, right? And what was the answer? The answer was basically true, right? Right? And the main reason why it is the case is that if you, again, go back to the definition of what it means for B to be complete. So B is complete if and only if for all elements x and y, either x is related to y or y is related to x. B is total if and only if for all x and y in x, if x is not equal to y, then, right, either x is related to y or y is related to x. Okay, so you can see that totality is a weaker property than completeness, because completeness, there's no restrictions on when completeness applies, right? So it applies for all pairs of x and y, whereas totality applies only when x and y are distinct. Okay, so since completeness applies for completeness, since this applies for all pairs of x and y, it also applies when x and y are not distinct, as well as when x and y are distinct. So the completeness covers additional cases that totality does not cover, namely the cases in which x and y are distinct. Right? Namely the cases when x and y are not distinct, I mean the same. So here, consider the example, we have A and B, and consider the example like this. Okay, so this example shows that the relation is total. Yes. The reason why that is so is that for all distinct pairs, there is an arrow coming from one direction or the other. But it is not complete. Why? Because in order for it to be complete, it has to apply to all pairs, including pairs that include the same element, meaning that we would need to have an arrow that is directing towards itself for each of the elements, right? So this kind of like basically implies that if B is complete, we would need each of the elements having an arrow that is pointing to itself. And whenever that is so whenever each and every element has an arrow that is pointing to itself, that means each and every element is related to itself, meaning that B is reflexive. So this is an implication that is true, okay, which we will soon see again. All right, so let us look at the converse of the previous statement. And actually, I've already explained this. Suppose that the binary relation is total. Does that imply that it is complete? And again, we have already seen by the example here where A is related all right, so there A, B. Let's kind of like look at a three element example to give a different example. So suppose consider a relation that goes something like that. Okay, so we can see here that the relation is total, right? And the reason why that is so is that for every pair of two distinct elements, there is at least one arrow that is coming from one element to the other, right? So if you look at A and B, A is related to B. If you look at to B and C, C is related to B. And if you look at to A and C, we can see that they're both related to each other, right? So it is total, but it is not complete. And the reason why that is so is that, as I have explained in the previous slide, in order for the fact that a binary relation is complete implies that it is reflexive, meaning that in order for it to be complete, we would need these arrows that are pointing towards itself for each of the elements. Okay, so since this is an example that shows that there could be a binary relation that is total, but that is not complete, this implication is false, right? False. Again, if it is complete, then that automatically implies that the relation is total, because completeness is a more general condition. So it applies, it says that the two elements has to be related one way or the other, regardless of what those two elements are. And it does not rule out, and it also covers the cases when the two elements are the same elements, whereas totality only applies when the two elements are distinct. So this is actually false. Sorry about that. So this is actually false. I'll change that later on. So this has to be false. Okay. Now consider the statement: if B is complete, then B is reflexive. Again, this is a statement that I have already explained, and this is true, right? And to explain the same thing again, if you look at the definition of completeness, the definition of completeness basically says that if B is complete, this basically means that for all x and y either x is related to y or y is related to x or both. Okay? And since this is a universal quantifier applying to all pairs x and y, this also implies the case when x and y are the same elements, right? So in particular, this basically implies that x is related to x or x is related to x. And we can simplify this statement as saying for all elements in x, x is related to x, which basically implies that B is reflexive. Okay. So it is true. Okay, so now let us consider the statement. Suppose that the binary relation B is asymmetric. Does this imply that the relation is irreflexive? Okay, so we can also use the definition, and from the definition we'll try to see whether the statement is true, right? So again, consider what the definition of asymmetry was. So a binary relation B is asymmetric if and only if for all elements x and y in X, the fact that X is related to Y implies that Y is not related to X. Okay? So from this is logically equivalent to, by material implication, not X be Y or not Y be X. Oh, no, okay, so, okay, sorry. And by De Morgan's law, we can pull out the negation symbol outside the parenthesis, which will make the statement not X be Y, and the conjunction changes into, disjunction changes into a conjunction, and Y be X. Okay? But you can also see that X and Y could be anything in set X, which means that this universal quantifier implies that the whole statement applies even when X and Y are the same thing, right? So basically, this implies the whole statement implies to the special case when X and Y are the same. So for all elements in X, it is not the case that X is related to X and X is related to X. But this can be simplified to X be X with the negation symbol here. So the statement implies that for all element X in X, x is not related to x, which is the same thing as saying that B is irreflexive. So the implication here is going to be true. Okay. Okay. So now consider the statement. Suppose that the binary relation is not symmetric. So it is not symmetric. Does this imply that the binary relation is asymmetric? Okay. So again, if you're confused about this, it is always best to work with the definition and see precisely what it entails. So B is symmetric. This basically means, if and only if, for all elements x and y in B, x be y implies y be x. Okay? But again, we can sort of like change this by material implication as saying not x be y or y be x. Okay, so suppose that B is not, okay, B is not symmetric. Then this basically means y. Okay, so for some reason the ink is not right. This basically means that it is not the case that for all x and y, and so this should be x and not y. Not x be y or y be x. Right? So we can again move the negation inside the quantifier 2 steps and change the universal quantifier, which will give us the statement okay. There exists an x in x, and there exists a y in x, such that it is not the case that not x be y or y be x. And from this, we can again use De Morgan's law to insert the negation sign inside the parenthesis, which we will get not x be y and not y be x. So the double negation here is going to cancel out, and this reduces then to the statement that there exists an x and that there exists a y, both in a set x, such that x is related to y, but y is not related to x. Okay? And we can see that this is saying something different from saying that the relation B is asymmetric, which basically says that there exists no pair of elements that are related to each other in both directions. Okay, so this is different from saying B is asymmetric. Okay, so here it is an example. Suppose that we have A and B and C. And suppose that we have A is related to B and B is related to C. And yes, consider this example over here. Okay, so we can see that the relation is not symmetric. And the reason why it is so is that although B is related to C, C is not related to B. So here, the relation is not symmetric. But we can also see that the relation is also not asymmetric. Because we can see that there exists a pair, namely A and B, in which they are related to each other in both directions. Okay? So basically, okay, so the reason why it is not symmetric is because of the case between B and C. And the reason why this relation is not asymmetric is because there are arrows pointing to both directions between the two elements A and B. Okay? So the answer is false. Okay, so let us now consider the converse of the previous statement. Okay, so consider the statement: if B is not, suppose that B is not asymmetric, does this imply that B is symmetric? Okay, so again, we use the definition. So again, recall what it means for B to be symmetric, to be asymmetric. So B is asymmetric basically means if and only if for all elements x and y in X, it is not the case that x, y, and y is related to x. Okay, now suppose that B is not asymmetric, then this basically means that it is not the case that for all x in X and for all y in X, not x be y and y be x. Again, we can move the negation inside the quantifier by 2 steps, and each time the universal quantifier is going to change into an existential quantifier. So this will basically make the statement: there exists an x in X, and there exists a y, another element in X, such that it is not the case that it is not the case that x be y and y be x. And we can basically cancel out the double negation. So the final statement will basically mean there exists an x and there exists a y in x such that x and y are related in both directions. And we can see that this is different from the statement that for all x and y in x, x and y are related to each other in both directions, which is the definition of B is symmetric. Right? So again, the mere fact, this shows that the mere fact that a relation is not asymmetric does not necessarily mean it is not the case that B is symmetric. Okay? So here is an example. So A, B, C. So okay, so you can see that this example is not asymmetric because why? This is not asymmetric. And the reason why that is so is we can see that there exists a pair that are related to each other. So it's not asymmetric because of this example here. But we can also see that it is not symmetric either. And the reason why that is so is that there exists this pair here. So in this pair, we can see that B is related to C, but C is not related to B. So it's not symmetric. So the statement is false. All right, so here is one which I think some people find it a little bit tricky, but it's important to understand this. So suppose that the binary relation B is asymmetric. Does this imply that the binary relation is anti-symmetric? Okay, so again, it is important to understand the precise definitions of these two properties of asymmetry and anti-symmetry. So remember that a binary relation B is asymmetric if and only if for all x and y, the fact that x is related to y implies that y is not related to x. And we have already seen that this is the same as saying that it is not the case that x is related to y and y is related to x. Okay? So that is what it means for a binary relation to be asymmetric. So what does it mean for a binary relation to be anti-symmetric? So a binary relation is anti-symmetric if and only if for all elements x and y, right? The fact that x is related to y and y is related to x together imply that x and y are identical. Okay? So this is the definition of anti-symmetry. So look at this for a moment. and you'll discover something. Meaning that, so the statement is that suppose that B is asymmetric. It means that B is asymmetric here. And according to asymmetry, this implies that for all elements x and y, it is not the case that x is related to y and y is related to x. Okay? Now, look at the definition of anti-symmetry. According to this definition, it says that for all x and y, if x is related to y and y is related to x, then this implies that x and y are identical, right? So what this basically means is that if the binary relation is asymmetric, it can never happen that x is related to y and y is related to x, right? So this can never happen, right? Meaning the antecedent of the definition of anti-symmetry is going to be what? If the binary relation is asymmetric, the antecedent of the definition of anti-symmetric is going to be always false, right? It's going to be always false. And remember that when the antecedent of false for any conditional statement, right? Remember the truth table of the conditional statement that Q implies P implies Q, and we have P and Q. Remember TF. So let us reconstruct the truth table of P implies Q. So we have seen here that whenever the antecedent, whenever the antecedent P is false, this implies that the entire conditional statement is true. And we can see here, if the binary relation B is asymmetric, that implies that the antecedent of the definition in anti-symmetry is always false, meaning that this whole statement is going to turn out true whenever the binary relation B is asymmetric. Therefore, if a binary relation is asymmetric, then it does imply that the binary relation B is anti-symmetric. So the question, the answer is that it is true, but it is true in a empty sense, right? And because it is true because the antecedent of anti-symmetry when the binary relation is asymmetric is always false, right? So there are no cases in which the antecedent of the definition of anti-symmetry gets met. And whenever that is the case, we say that the statement is vacuously true, meaning that the antecedent of the conditional statement is never met. Okay? Okay, so let us now consider a converse of the previous statement. So the statement is asking whether, suppose that the binary relation B is anti-symmetric, and the question is whether this implies that it is asymmetric. Okay, think about this for a moment. And since we have already defined the definition of the true properties of anti-symmetry and asymmetry, we'll kind of like just display the answer right away. So it is false. And the question is Why is it false? Can you show why this is false? And here, we'll try to show that the statement is false by presenting what's known as a counterexample, right? And a counterexample is basically an example that can be used to prove that a given conditional statement is false, right? So basically, it's an example. So a counterexample is for a given conditional statement right? A counterexample, a example is an example that makes the antecedent true while making the consequent false. Okay? So a counterexample is an example that shows an example that makes the antecedent true while making the consequent false. And when you show a counterexample, it proves that the conditional statement is false. Right? And this is because a conditional statement is false only when the antecedent is true and the consequent is false. So if you provide a counterexample, this basically shows that that could happen. Okay? So let us try to prove that this conditional statement that says that if the binary relation is anti-symmetric, then it is asymmetric is false. And consider the example here. So suppose that there are two elements, A and B, and we have this kind of relation, right? So we can see here that the relation is anti-symmetry meets it's anti-symmetric, yes. However, this is not asymmetric. And why is it not asymmetric? Remember that we have seen that that a binary relation is asymmetric. If a binary relation is asymmetric, this implies that the binary relation is irreflexive, right? What this basically means is that irreflexivity is a necessary condition for asymmetry. Okay? So In order for any relation to be asymmetric, it has to first be irreflexive, which means that if a relation is not irreflexive, then it can't be asymmetric either. Now, look at this example here, right? This example basically shows a relation, right? A relation that is not irreflexive, okay? And since it is not irreflexive, it cannot be, this implies that it is not asymmetric. And this is because asymmetry implies irreflexivity. So in order for anything to be asymmetric, it has to first be irreflexive. And since this binary relation is not irreflexive, it can't be asymmetric, okay? So the point is that here's a relation that is anti-symmetric, but since this relation is not irreflexive, it can't be asymmetric. Therefore, the fact that the relation is anti-symmetric does not imply that the relation is asymmetric, right? Therefore, the statement is false. Okay? Okay, so here's a list of a number of results. Some of them we have already proven, and some of them I'll pick a couple of them and prove them a little bit later. But let's just look at all the statements that are true. And we call those statements that can be proven to be true by the initial axioms or definitions to be theorems. So here's theorem 1.1. If a relation is complete, then it is reflexive. We already proven that. Theorem 1.2, if a relation is asymmetric, then it is irreflexive. We have already proven that as well. The third one is if a relation is transitive, then the following, so a relation is transitive if and only if, right? So here, it's a biconditional statement, meaning the implication goes both ways. So what this basically says is that if a relation is transitive, if and only if, for all natural number n, and for any arbitrary n number of elements that we pick from the set X, if the first element, x1, is connected to x2, and the x2 is connected to x3, until we reach the final element. So the n elements are concatenated into this long chain that connects the first, the previous element to the subsequent element by the binary relation B. Then this basically implies that the first and the last one, right, is also connected as well. So the first one and the last one is connected. So if the first one is connected to the last one through this series of chains of connections, then the first one and the last one is connected. So we're going to prove this in the next slide, but let's move on. If B is negatively transitive, then for every x, y, and z, the fact that x is related to y implies that z, either x is related to z or z is related to y. Okay, so actually we have seen that the definition of negative transitivity is a bit cumbersome to actually apply in practical usage. So this would actually become much more handy when you want to see and examine whether the relation is whether negative transitivity is satisfied in a given relation. So what it basically says is that if any two elements x and y are related, then the third element z has to be related to either x or y in this way. Okay, So we're going to also prove this a little bit later. So the fifth result is that if a relation is anti-symmetric and negatively transitive, then it is transitive. And the sixth one is that if the relation is complete, if and only if it is irreflexive and total. And the last one is that if a relation is total and transitive, then it is negatively transitive, right? So all of these results can be basically proven by the definition of all of the properties of the binary relations that we have defined previously. So it's a very good practice and an exercise to do on your own. So these three are not going to be, I will not prove these three in class, but it would be good practice for you to do it on your own. Okay, so now among them, let us prove Theorem 1.3. And again, Theorem 1.3 states the following. A binary relation is transitive if and only if for all natural number n and for any n arbitrarily chosen elements in X. And if we labeled the n elements from x1 to xn, if x1 is connected to xn through this chain that connects each element to the element with this subsequent index by the binary relation b. So if x1 is related to x2 until through this long chain that eventually reaches xn, then the first x1 is related to xn as well, right? So remember that this is a biconditional statement. So it consists of this direction and this direction. Okay, so in order to prove these kind of like if and only if statement, right? So if this is if, so right, so this is basically if and only if statements. It is important to prove both directions. Okay, so we will, in this slide, we'll basically prove the more easier direction. That is the direction that if this long thing holds, then the binary relation is transitive. So let's look at the proof. Okay, so to prove it, we assume that the antecedent, right? So we're proving this direction here, right? So the antecedent is going to be this long expression here. So suppose first that the antecedent holds, right? Suppose that that is true. So since the antecedent holds, and the antecedent basically states that this here is true for all natural number n, the claim basically holds in particular when n is 3, right? So we have, since let us say that this long statement here is star. Since star holds, it holds in particular when n is 3 because it holds for all natural number n, right? So what that implies is that for any three elements, x1 and x2 and x3, if we connect x1 to x2 to x3 by the binary relation 3, this implies that x1 is connected to x3 by that binary relation. And we can see that this exactly is the definition of transitivity. Transitivity, okay? So in other words, the binary relation is transitive, and that basically completes the right to left direction of the proof. Okay, so let us now continue to prove Theorem 1.3, and this time the more complicated and difficult direction. So here is the statement again. Okay, so now we're going to prove that if the binary relation is transitive, then this long statement, which we okay, so this long statement holds. All right, so to prove this, we need to basically use a mathematical proof technique called mathematical induction. Okay, so what is mathematical induction? So mathematical induction is basically a proof technique we use. It's a proof technique that we use when we want to prove that some statement, that is, some statement holds true for all natural numbers n. Okay, so that is, some statement holds for all natural number n. So for example, suppose that we want to prove the statement for all natural number n, Pn is true. Okay, we want to prove that. And to do this, we basically, if we are using mathematical induction, we proceed in the following two steps. We can prove this by the following two steps. The first step is called what's known as the base step, and in this step, we basically show that the statement is true for n equals 1. In other words, we basically show that P1 is true. Okay. Next, in the inductive step, we basically show that if the statement is true for some natural number k, and this can be arbitrary, so if it is true for some natural number k, then this implies that the statement is true for the natural number k plus 1. That is, in the inductive step, we basically show that this conditional statement is true, that pk implies that pk plus 1. Okay, so in the base step, we basically show that p1 is true, and in the inductive step, we basically show that pk implies pk plus 1. So if we go through the base step and the inductive step, this basically proves that the statement Pn is true for all natural number n. Okay, so if you establish these two steps, then this shows that the statement is true for all natural. You have basically proven for all natural number n, Pn is true, right? So can you guys all see why this holds? By the base step, it is established, right? So here is the basic logic of why this works. So in the base step, you have established that P1 is true. Okay? So by the inductive step, you have established if Pk is true, then Pk plus 1 is true. But together with the fact that you have established from the base step, this implies that if P1 is true, then P2 is true, right? So, and if you know that P2 is true, by the inductive step, you know that P3 is true, and so forth, for all natural number n. And that's basically why mathematical induction works. Okay, so let us now use mathematical induction to prove Theorem 1.3, the hard direction, right? That if a binary relation is transitive, then this implies that for all natural number n, this holds. Okay? So we're going to prove this by using the technique of mathematical induction that we have just that I have just explained in the previous slide. So whenever you prove a conditional statement, what you do is you first assume that the antecedent is true, right? So the antecedent here is that the binary relation is transitive. So what you do is you first suppose that B is transitive, and what you need to show is that the fact that B is transitive implies that for all natural number n, this whole statement is true. So to do this, let us define the predicate function Pn, and this basically denotes the statement that says that for any n elements of x, if x1 is connected through the chain of binary relation B, to xn by this implies that the first element is connected to the last element by the binary relation B. Okay, so we basically wish to show that Pn is true for all natural number n, right? So basically we can see here that this part here is Pn. So we can see that what we want to show is that we want to show that for all natural number n, Pn is true. Okay? So first, suppose that n equals 1 and P1. And P1 basically claims that for every element, the x1, so this should actually be just, since we have this, so this should actually be simply written as x1 simply implies x1, which is trivially true, right? Now, suppose that pk is true. Pk is true for some arbitrary natural number k, right? For some. Now, consider, let's pick any k plus 1 elements from x1 to x2 to xk plus 1, okay? Xk plus 1. And suppose that x1 is connected to xk plus 1 through this chain of binary relations that are this chain of concatenations that relate each element by the binary relation B. Okay, so we have x1 is connected to x2, which is connected to x3, and so forth to xk until xk plus 1. Okay? So, right. So we have assumed that pk is true, right? Okay. Since pk is true, we have here, right? So remember that this long chain is a chain of conjunctions. So we can look at this conjunction that connects from x1 to xk by itself. But since pk is true, the fact that we have this long chain from x1 to xk basically implies that the first element is related to the kth element by the binary relation k. Okay? So basically what this shows is that this part here implies that x1 is connected to xk, right? So what we now have here is that we have x1 be xk, and we also have xk be xk plus 1, okay? So we have something like this. But since we're assuming that the binary relation B is transitive, since B is transitive, this implies that x1 is related to xk plus 1 by binary relation B. Okay? And that's basically what we wanted to show. Okay? So the truth of pk implies the truth of pk plus 1. So here, so up here, this was the base step. And here, we have established the inductive step. And by using mathematical induction, we conclude that the statement Pn is true for all natural number n as desired. And that basically proves the statement. Okay, so try to go over this on your own and try to understand each step that is contained in the proof, and do not move on to this next sentence until you are completely convinced of what each step in the proof is actually doing. Okay? All right, so now let's prove Theorem 1.4, which basically says that if a binary relation is negatively transitive, then for all x, y, and z, xby implies xbx or zby. Okay? So to do this, we'll basically prove, so what this statement is basically trying to establish is the logical equivalence of negative transitivity and this statement here. Okay, it's trying to show that they are logically equivalent. So to do this, we'll basically go through a series of biconditional proofs by supplying and substituting logical equivalences from and so forth. All right. So suppose that the binary relation is negatively transitive. Then this is the same as saying that for all x, y, and z, not xz and not zy implies not xy. All right. Not xz and not zy implies that not xy, and this is simply by the definition of negative transitivity. Now, from this contraposition, we take the contraposition of this conditional statement, right? So the contraposition, if we have the conditional statement P implies Q, this is logically equivalent to its contrapositive, which is not Q implies not P. Okay, so we are basically doing the same thing here. So what we're doing is that we are negating the consequent and moving it to the antecedent, and we are also negating the antecedent and moving it to the consequent, right? So basically, by taking the contrapositive of the definition of negative transitivity, we arrive at the statement that says for all x, y, and z, not xby implies not xy and not zby. Okay, so we can see here that we have double negation here, and we can also use De Morgan's law at this point. Okay, so first we take the double negation over here and make the statement like this, and this is by double negation. Next, what we do is we use De Morgan's law to basically distribute the negation sign into the parenthesis, right? So this expression by De Morgan's law changes into that. Okay? Then we apply double negation once again to this. So the double negation in this here gets cancelled, and this cancels, and we finally arrive at the desired expression that basically says that for all x, y, and z, xby implies xbz or zby. And what this basically means intuitively is that if a binary relation is negatively transitive, this simply means that if any two elements are related to each other, any third element has to be related either to the first element, so either the first element has to be related to the the third element, or the third element has to be related to the second element. Okay, so this basically ends the proof. Okay, so we have just proven this statement, the logical equivalence between negative transitivity and this statement over here. And the reason why this statement is actually very useful to identify whether or not a binary relation is negatively transitive, because the original definition of negative transitivity is a little bit cumbersome, and it's very difficult to apply in real examples. But the new definition here is much easier, and we'll basically try to see how this works. Now, consider two examples. So there's example 1, there's also example 2. So in here, suppose that we have there are 3 elements, A, B, and C. And the first example, the relation is like this. And the second example, the relation is like this. Okay? So the question is, let's first look at example 1. The question is this negatively transitive? And to apply the definition, what we need to check is that whenever any two elements are related, so we can see that A is related to C, A is related to C, A is related to C, right? Then any third element, either the first component has to be related to the third element, or the third element has to be connected to the second element, right? So we can see here that since the first element is related to the third element, it is negatively transitive, right? So it is negative. Yes, the answer is yes. Now again, so we can't establish this yet. We have to check again. So we can see that A is related to B. So in order for negative transitivity to hold, the third element C, either A has to relate to C or C has to relate to B. But we can see that A is related to C, so it holds. So since that exhausts all cases, we can say that it is negatively transitive. Now, let's look at the second example. Is this negatively transitive? And again, we apply the definition, the theorem that we have proven here. And this basically says, we can see here that A is related to B, right? And according to the theorem, when A is related to B, any third element, namely C, has to be such that either A is related to B or C is related to B, right? So either we need this line or this line. But since we do not have both lines, this basically shows that the relation is not negatively transitive. Okay, so the answer is no. So as we can see, using this theorem makes it much more easier to identify whether a given binary relation is negatively transitive or not. Okay, so thank you very much. This ends the lecture.